Much, chairpersons. I'm very pleased to be here today, rather than back in Virginia, where I probably would be pedaling a boat around someplace. This is going to be much more fun. I'm here to talk to you on behalf of a project that my student Yi and I have been working on for a couple of years now. We are focusing on the magnetic sensing of nanoparticles, basically, as a mechanism that will allow us to measure biological agents on an integrated circuit. So we're looking to develop a single chip implementation of a biosensor that can be used in a typical laboratory environment where we have a very controlled environment and we can readily set up the whole process and procedure, but we also are looking forward to being able to have a device that can be used in the field as well. A sensor that through the use of MEMS can have a sample delivered to it, and on the fly we can make some measurements. The idea in implementing the system is that the sensing and calculations will all be done on a single chip, that the process will be quite high speed. As a matter of fact, we'd like to be have it be as much real-time or as little delay as possible once a bioorganism has been sensed. And we need to have both the high accuracy as well as high sensitivity, or at least a settable sensitivity. And those are the goals that we start the project with. Here's a real simplistic schematic of the way in which the system is going to work. We have some containers, sample containers, that will be sensitized to various organisms. We have the sensor containers connected on the same chip to some digital circuitry that will form the detection electronics, all integrated into the same piece, and there may be several of these kinds of sensitive containers so that we can look at different types of organisms. The mechanism for sensing is an inductive sensor. On the next slide, we kind of have a big schematic of it. The idea is that we have a very basic inductor here that feeds information into an oscillator whose frequency is controlled by the inductance that we see in the coil out here. And then there's a digital counter out here that determines the characteristics of the information passed to it or inferred by the inductance. The basic idea in here, although it's not apparent from this figure, is that the inductor would have more or less numbers of particles of nanoparticles inside the container. So there would be an inductive change. We would start off with an empty container, make a measurement, set a baseline. We would introduce nanoparticles into the container, change the inductance. The number of nanoparticles that are introduced would be directly proportional to the inductance. A change in the nanoparticles is directly proportional to the change in inductance, and that relates back to the frequency. And so as we work our way through the chain, we'd be able to basically set this thing up so that we could be able to calculate the number of particles that have changed inside of our container. Here are a couple of pathogens that we've looked at. We've embedded them with nanoparticles and seen various characteristic changes, but we are working with the folks in our School of Veterinary Medicine to characterize the uptake of nanoparticles in things like typhi, in things like anthrax here, to be able to catalog the biological portion of the sensor. So this kind of is a schematic representation of what we're doing with the antibodies. We sensitize the surface with a number of antibodies. We are able to attach to that surface pathogens that have iron particles attached to them. And again, what we're trying to do is to get a measurement of the number of iron particles and thus infer by the uptake of each of the antigens the number of antigens that have actually been placed into the container. Sensor head, again, looks like this. This is kind of a single turn sensor head. single level coil sensor head, where we've wrapped the turns in a rectangular form around the container. It turned out that this simulated okay, but doesn't give us the kind of characteristics that we need. And in fact, we were looking to be able to increase the sensitivity, and to do that we had to increase the inductance of our container. So what we ended up doing was looking at a multi-wire layer inductor built into the coil. You can see schematically again what this looks like as we wrap the number of coils around the overall sensor container. And the number of turns that we have here increases the inductance, and of course increases the sensitivity of the overall sensor head. This is a simulation output of looking at the magnetic fields that were generated by a single layer and some multi-layer inductors that were placed around these shapes. In this rectangular shape, the field indications that we get from simulation show a relatively uniform area in the center indicated by the blue, but around the edges, as might be expected, we see some red high intensity. The greens here indicate a lower intensity, and of course yellow is our transition over to the blue area. What we'd really like to see is across the entire sensor medium a uniform field, and we'd really like to see it all be red, because the higher the intensity of the field, the more inductance we have, and that increases our sensitivity. Unfortunately, this non-uniform field leads us into problems, because depending upon placement of the iron particles, we end up having different sensing. As we looked at alternate coil shapes and multi-layer versus simple coils, we started off by doing what we could do rather easily, which is to put the coil into this shape. And again, we have a nice area in the center which has a fairly uniform field, but we still run into problems out on the outer edges where it's difficult to say which part of the field a particular group of antigens may have fallen into, and thus whether or not they are going to cause a large or a small change in inductance as they fall into those portions of the field. The circular inductor has a similar problem, and by the way, this is again of the multiple layer strategy that looks like this, where layers are placed one on top of another. So those coils work, but we get a somewhat reduced area that is sensitive. And the next thing you might think is, well, why not make the coil just larger and increase by virtue of the overall increase the area that has a uniform field? The problem with doing that is that the field in the center then becomes reduced. And so the thing we have to do is to kind of keep it as small as possible, as tight around the samples as is possible, yet still have a uniform field as much as is possible. If you look at the H field variations by altitude, because in fact if you go back to this container here and you call this direction, the vertical direction here, the altitude, as you move the bottom of the sample container up and down, you have variations in the intensity of the field. Not only do you have these lateral variations that cause us some problems, but you have some variations vertically. Now this is not bad here in the middle. As a matter of fact, all the lines kind of converge in this simulation and show that this would work out pretty well altitude-wise, but it doesn't last laterally long enough. And as a matter of fact, as you get out into these fields here, we've got some real problems. The percentage change in the field across here gets as high as 30 to 40%. And so that variance, again, causes us a problem, because if you think about putting a nanoparticle of iron out into the field in this area where these variations occur, if you place it at different altitudes, you will look like you may be detecting 1 or 2 or 3 nanoparticles, depending upon whether you get into the low field or the higher field areas. And that's what we're trying to eliminate. So next simulation, we adjusted the coil shape, and we did a little bit with that in terms of where we place the wires. If you look down here at the bottom, this diagram corresponds laterally with the plots up above, and the purple colorations here indicate pieces of wire, and the cross-section of wire that would be in a circular form going into the board and around. Okay, and there's variation in the width of the wire. A somewhat narrow wire here, slightly wider, and a little bit wider. And we get into, gee, that looks like an awful pattern. As a matter of fact, it's probably worse than what we saw before because we have now problems with altitude as well as lateral problems. Depending upon where you place the particle, you can seem to detect one or more particles. We clean this up a little bit by, again, making some variations in the wire. If you go from one back to the other, you'll see that we've changed the width and placement of the wire, and the simulation results give us a little bit cleaner pattern, and that's great. That's what we're headed for. If you go to a more complete result where we have now multiple layers, in this case 1, 2, 3, 4, 5 layers of wire. So we've got 5 layers of wire, and in each of the layers we have 2 different coils that wrap around, and we have variations in the width of the wires we go across. Well, we're doing pretty well laterally here, and not too bad in terms of the vertical changes in the field intensity. So, the best curve of all of these is probably this blue curve, and that kind of sets us up for where we'd like to put the bottom of our container. Because what's going to happen is down in the center of this thing, we're going to drill down into the silicon using processing techniques to set the bottom of the container so that as the antibodies sit on the bottom of the container and hold the antigens that have iron nanoparticles on them up into the space, they coincide with, as much as is possible, the blue curve. And the container would sit something along those lines with respect to the altitude of the wires down here. Now this is a disjoint set. This space here is really at the bottom of this space right here. So that's kind of where we want our particles to end up sitting, right along that blue curve, and so we have the best sensitivity. Let's see. After doing some testing and introducing 50 nanometer nanoparticles, iron nanoparticles, 50 nanometer spheres, and we place them randomly around the container, so around this entire container, both vertically as well as laterally around. We end up with a curve that looks like this, which is what we're driving towards. Basically, if you look at the number of nanoparticles that were placed, and we look at the data points coming across here, the inductance change is linear with respect to the number of nanoparticles, which is great. So as you add another nanoparticle, you should be able to predict that you get a corresponding linear change in the inductance, which gives us a corresponding linear change in the frequency, which allows us to pick out the fact that we've added just 1 more particle, or 2 more particles, or a linear increase in particles. So, what does that mean for us? Well, if you look at what's going on in terms of numbers, we are able to, we found that each nanoparticle, the 50 nanometer spheres, causes about a 7% change in the inductance, and variations across the entire container for the randomly placed particles across the container indicate no more than a 3% change in inductance just by virtue of where they're placed. This is much better than some of the earlier sensors that were out there where we are seeing 25% changes as you moved across the field space. So we've improved a little bit, and we hope to do better with it as we build some of the, do the design for the oscillators and counters and perform some fabrication work. We'll do some testing. This is kind of the schematic for the overall system. We are at the point where we've done all of the magnetic simulations, some magnetic measurements. The oscillator, frequency counter, and data processing unit are actually designed, and we're waiting for our turn in the fabrication cycle to be able to bring some true results, experimental results out. So with that, I'm going to close and ask if there might be any questions.